Hello students, welcome to this video. The topic of our today's discussion is Introduction to Relative Atomic Mass, or what we call as RAM. Relative atomic mass RAM is represented by capital A and subscript is small r, which means relative. Mass is represented by capital A, and if I write subscript small r, so it will give me with relative atomic mass. Now what is relative atomic mass? It is the weighted average mass of an atom's isotopes. We studied in the previous lecture about isotopes. Now if I consider carbon, it has two main isotopes, carbon 12 and carbon 13. We do not consider carbon 14 because it is radioactive. So the average mass of all the isotopes of an atom is what we call as relative atomic mass. It is measured relative to the 1/12th the mass of carbon 12 atom. That means carbon 12 is the basis here. Why? Because it is easily available. That means it is present in more amount. It is present in abundance in the nature. That's why carbon 12 is considered as the basis for calculating relative atomic mass. Why do we need to study relative atomic mass? Because it is essential in understanding the atomic properties and reactions. Now, what is relative atomic mass? It represents the average mass of isotopes of an element, accounts for the natural abundance of each isotope. Why? Because we will be requiring the natural abundance of each isotope in calculating the relative atomic mass. For example, carbon's relative atomic mass is 12.01, but we actually consider it as 12. Why use relative atomic mass? It simplifies the comparisons of atomic masses across elements. Secondly, it provides a standard for chemical calculations. For example, for carbon, we take it as 12. So it can simplify our calculations. Then it is essential for determining the molecular masses too. Now, understanding isotopic abundance. What is isotopic abundance? It refers to the percentage of each isotope in nature. How much amount of that particular isotope is found in the nature is what we call as isotopic abundance. Different isotopes contribute differently to the relative atomic mass because different isotopes are found in the nature. Their percentage is different in the nature, so they would contribute differently to the relative atomic mass. For example, chlorine has two isotopes, Cl35 and Cl37. Now, what is the formula for calculating relative atomic mass? It is given by AR is equal to summation of, this symbol represents summation of isotopic mass into abundance upon 100. If I simplify this formula, we can write it as RAM is equal to the mass of isotope 1 into its percentage in the nature plus mass of isotope 2 into its percentage upon 100. And if there are three isotopes, so the formula would become plus mass of isotope 3 into its percentage. So we can calculate according to the number of isotopes, right? Now, each isotope's mass is multiplied. Each isotope's mass is multiplied by its relative abundance. That means in how much amount it is present in the nature. The weighted average gives us the relative atomic mass, or RAM. Now, example 1, carbon isotopes. We know that carbon has two isotopes, carbon 12 and carbon 13. So if I were to calculate the relative atomic mass of carbon, how would I calculate? Mass of carbon 12 isotope 1, that is carbon 12 mass is 12 into its percentage found in the nature is 98.9. The percentage would be given to us in the question, so no need to worry about that. Plus mass of carbon 13, that is isotope 2, is 13 into its percentage is 1.1 upon 100. Now 12 into 98.9 would give me with 1186.8 plus 13 into 1.1 would give me with 14.3 upon 100. Now 1186.8 plus 14.3 would be 1201.1 upon 100, and this would give me with 12.011. So this is how we can calculate the relative atomic mass of different elements. It reflects the weighted contribution of each isotope. Here we have taken into consideration each isotope, the mass and its percentage as well. Right? Now, example 2, chlorine isotopes. Now, chlorine has two isotopes, Cl35 and Cl37. Percentages are given to us, so we can directly calculate RAM. Now, mass of chlorine 35 would be 35 into its percentage is 75. Mass of 37 isotope is 37 into its percentage is 25. We'll add them, and this would give me with 35.5. That's why we take the mass of chlorine as 35.5, because it is the average mass of both these isotopes of chlorine. It explains why chlorine's relative mass is not a whole number. Yes, 35.5 is not a whole number. And why 35.5 is coming? Because it is the average mass of the isotopes of Cl35 and Cl37. That's why it is not a whole number. So isotopes can explain this, that why chlorine's relative atomic mass or chlorine's mass is not a whole number. Now, role of mass spectrometry. Mass spectrometry measures isotopic masses and abundance. The isotope's mass and its abundance is measured by mass spectrometry. It provides precise data for calculating the relative atomic mass, because we would be needing the masses and abundances of isotopes to calculate the relative atomic mass. Widely used in analytical chemistry. Now, what are the applications of relative atomic mass? It is used in stoichiometry for balancing the chemical reactions. We would be needing the mass. It is essential in determining the molecular and formula masses. Also, it supports accurate chemical analysis and research. Now, relative atomic mass versus atomic number. Atomic number is the number of protons in the nucleus, but relative atomic mass accounts for isotopes and their abundance, because we take into account the mass of the isotope and their abundance. But there is no role of isotopes in calculating the atomic number. They are just the number of protons. Both provide critical information about an element. Now, limitations of relative atomic mass. Limitations include that it assumes the isotopic abundances are constant. The abundances that we take, it assumes that they are constant. For example, 75, 25, 35. Variations in isotopic composition can affect the calculations. If there are variations in the composition or the percentage found in the nature, so it can affect our calculations. It requires accurate experimental data for precision. If we need to accurately predict the relative atomic mass of a particular element, we require accurate experimental data which can tell us about the isotopic abundances correctly. Calculating with weighted averages. Relative atomic mass is a weighted average of atomic masses. This we have studied. Emphasizes the contribution of abundant isotopes more. Which are abundant, they are emphasized more. The isotopes which are abundant in nature. For example, in case of carbon 12 is more abundant. So we emphasize on that more. Important for calculating the compound properties. Importance in chemistry includes crucial for predicting reaction outcomes in the chemistry. because it requires stoichiometry. So we need to consider this for predicting the reaction outcomes. It supports qualitative analysis and material design, helps us to understand the periodic trends in the elements in the periodic table. Now, one practice problem is given here. We need to calculate the relative atomic mass of an element with isotopes X20 and X22, and their percentages are also given to us. So, RAM would be equal to mass is 20 of first isotope and its percentage is 60, plus mass is 22 into percentage is 40 upon 100. Now 22 into 60 would give me with 1320 plus 880 upon 100. Now 1320 plus 880 would be 2200 upon 100. This would give me with 22. So this is the, okay, so here the mass is 20. I have taken 22. This would be 20. And 20 into 60 would be 1200. 1200 plus 880 would be 2080. And 2080 divided by 100 would be 20.8. So this is the relative atomic mass of that particular element. It ensures proper handling of percentages in calculations. Now, summary. Relative atomic mass is the weighted average mass of isotopes. It simplifies our chemical calculations and comparisons. Mass spectrometry is used to determine the relative atomic mass, as it gives us the abundances and masses of the elements. Applications include research, industry, and medicine. I hope you got all these points. Thank you.